I guess we can move to the next topic then. Let's take a look at the encoder decoder. This is your English sentence. That's your French sentence. You're encoding everything inside a vector, and then you're using that vector and decoding it to give you the translation. So that's for the big picture. And the details could be LSTMs, GRUs, attention models, whatever that you do. So these are the details, but that's the big picture. There is still this question that is bothering us. Why are neural networks, at least at that time, are not able to surpass the performance of classical machine learning techniques? And this paper is going to try to study and see what's wrong. Could it be that the sequence length matters? Could it be that your recurrent neural network is forgetting some information? Or could it be your vocabulary? Maybe there are many unknown words in your vocabulary that you don't know. Maybe your vocabulary matters. So this paper will try to address both of them, at least study them and see what is the performance loss. And then at the same time, there is a nice architecture here that is being introduced. I want you to know about that as well, about the details of the encoder. The decoder is still the same. It's a recurrent neural network, but the encoder, you have multiple options. This is a recap of what we did before with recurrent neural networks. You have a variable length input sequence, like economic growth has slowed down in recent years. Then you're gonna, whatever F is, that's gonna be your recurrent neural network. And you can model this to be a GRU or LSTM, and that's gonna give you your hidden state. F could be a fancy activation, like what you saw before with GRUs. You can have a reset gate, you can have an update gate if you're using GRUs. And visually speaking, this is how things are gonna progress in time. You take two words, you combine them together, that's gonna give you a hidden state. That's your HT minus one. XT goes in, you're gonna combine them together, that's gonna give you HT. Now you rename things. This is gonna be HT minus one, this is gonna be your XT. You do the same thing and you're sharing parameters. So these arrows are shared. And if you have a fancy activation function, like GRU, that's how it's gonna look like. That's how people usually visualize it. I don't like it that much. I like the math more, but you can actually try to visualize. There is a reset gate, there is an update gate. So the reset gate could be sometimes open, sometimes closed, or partly open, partly closed. And then the information is passing from one state to the next state. At least if you want to use that for language modeling, this is what's gonna be your probability. Why am I talking about language modeling? Because it's gonna help me introduce language modeling, what the task is, and it's actually helping us not worry about the decoder part. For language modeling, this is gonna give you your loss, and then you're gonna optimize it with respect to the parameters of your neural network. And you can actually try to model this using a softmax. So I didn't want to talk about the decoder part. That's why I stopped with the language model. But we know how to add the decoder and how to train it, how to train the entire system end to end. But there is another architecture. You might say maybe for the encoder, you can use convolutional neural networks. And there is this idea of gated recursive CNNs. It's a convolutional neural network that you are sharing parameters at each level of the convolution. So you can have multiple layers of convolution, but now you're sharing the parameters from one layer to the next one. Again, the same thing is gonna happen, input sequence. You're gonna have a bunch of activation functions or activation outputs or activated hidden units. J is gonna give you where you are in your sequence. J is gonna count 1 up until T. And then a level of your convolution, these are the layers, you're gonna count them by T. That's your index. This is how it's gonna look like. So J is gonna count from 1, 2, 3, 4, 5, 6. And then T is gonna count from 1, 2, 3, 4, 5. That's why you have T minus 1. Okay, so one of them is gonna go vertically and the other one is gonna go horizontally, J and T. Now we're gonna have a fancy activation. Now I'm talking about this panel B of the figure. Two words go in, this word and the next word, and then you're gonna have a gate, similar to the gates that you had here, but now your gate is gonna have 3 options. To attend to the information coming from the right word, to attend to the joint information from both words, left and right, and to attend to the information from the left. So one of them is right, WR. WR is the right, WL is the information from left, and WC is the information from the center. And you have an attention span of 1, attention budget of 1. It means that you're gonna have a softmax on these, WR, WL, and WC. What is H? You're gonna encode. So the first layer, H0, this is the first layer, is gonna take your word and then embed it. So always the first layer to a neural network for language modeling is the embedding. So that's why they are fundamental. And you have a softmax that's gonna tell you how you're gonna spread the budget of 1 among left, right, and center. And what you're gonna take as input is gonna be the embeddings from the previous layer at time j minus 1 and j, and you're gonna have information from left and right. So these are the parameters that you're gonna learn, GL, GR. And then what is the center information? What is H tilde? It's a linear combination of the first word, the left word, the right word, and then you're gonna push it through an element-wise nonlinearity. But the aim of this paper is not to introduce a new architecture. It's gonna tell you, regardless of the architecture, regardless of the encoder, whether you're using an RNN or a CNN, I want to study, or this paper wants to study, the effect of the sequence length and compare long versus short. This is qualitatively speaking. One cool thing about the CNN is that you're learning some nice patterns. So you're learning some nice semantics coming out of the model. And if you remember recursive neural networks that we covered it, that one could happen as part of this gated recursive CNN on the fly through training. So these sorts of pattern could appear, and that can encode some syntax. So syntactically speaking, this CNN is doing a better job. And wherever you see RNN encoder, that is when you're using the RNN here. And whenever you see GR-conv, that is gated recurrent convolutional neural network. And Moses, we know it's the baseline. So there are the long sentences, there are the short sentences, and the long sentences, regardless of the encoder that you use, you're gonna forget some stuff towards the end. This is your source translation, this is your reference translation. And then it turns out the length of the sequence matters. And if I remember correctly, one of you mentioned that the length of your sequence matters for classification. It also matters for translation. That was qualitatively speaking. Quantitatively speaking, let's take a look at the sentence length and compute the blue score on sentences of, for instance, length 10 or maximum of 10, or sentences of length maximum of 20. So basically what you're doing here, you have your entire data set, and then you are filtering out only the ones in your test data that have a length of less than 20. And then you're gonna report your performance of the blue score on those sentences. And as you increase the sentence length, the quality of the blue score drops significantly. So the length matters regardless of the architecture, whether you're using RNN encoder or you're using a convolutional neural network. So it happens regardless. And now let's study the vocabulary size. Again, the vocabulary size matters. If you have a lot of unknown words in your sentences, then the quality of your translation is going to go down. So what does this mean? It's pointing us to two directions that are important for improvement. One is the sequence length, the sentence length, and the other one is the vocabulary size. So you need to make some adjustments to your neural networks to address these two issues. So is everything clear? So this paper is posing problems. The problem was, why isn't the neural network beating the state of the art? And this paper is saying maybe these are the two reasons, the sentence length and the vocabulary size.
It makes me wonder if the loss in blue score is just due to like properties of the blue score itself. Like if even a human translation quality, like the gold truth, the score would decrease if the sentence length got longer.
Actually, if you remember, you're right. But in the blue score, we are trying to decrease the effect of the sentence length. when you had that brevity penalty in your
Mhm.
BLEU score. So you're actually penalizing the sentence length. If it's short, you're penalizing your BLEU score. You're pushing this down. Even after pushing the BLEU score down, you have that problem.
Yeah.
Okay.
And then the other question was just about the dimensions of these things. The G matrices output three-dimensional vector are WC, WL, and WR.
That's a great question. Yes.
They're scalars.
So this is a vector of the size that you chose.
Yeah.
That's a hyperparameter, but then you need to go to dimension 3.
So it's
3 by 100, 3 by 256, whatever. Okay.
Cool.
No, that was a good question. Any other questions?